Good evening, my name is Phil Williamson, and I am taking Dr. Buckner's MAE 535 class, Design of Electromechanical Systems, MAE 535, and my demonstration is on eddy current theory and how it applies to non-destructive testing. Now, a very common demonstration of eddy current is the dropping of a magnet down a copper pipe and watching the magnet move slowly. And the reason why this happens, of course, is due to the eddy current and also Lenz's law that talks about opposing magnetic forces or opposing electromotive forces. Okay? Even though this copper material is not magnetic, what happens when you drop a rare earth magnet, this is a rare earth magnet, down the pipe, is it moves slowly because of the magnetic fields between the magnet and the electric current that's being generated by the copper are opposing each other and moving in opposite directions and causing the magnet to fall slowly. Okay, and I'm going to demonstrate that right now just so you'll see. Okay, can you see to the bottom of the pipe? All right, here we go. All right. Now, non-destructive testing of pipe materials, this theory can be applied. Okay, and the most common way it's used is detecting defects in pipes and measuring those defects. Now, I've attempted to construct a simple eddy current test. This is only going to detect defects in the pipe. It's not going to measure them. I'd need a lot, more sophisticated equipment for that. But what I'm going to do is show how the principle of eddy current will, where, the magnet will behave differently as it goes down to the pipe with a lot of defects. And I've got a similar copper pipe, same length, they're both 2 feet long, but I have several gouges cut in the pipe. Okay. Now, just for demonstration, I'm going to drop the magnet straight down this pipe as well. Okay, are you ready?
Mm-hmm.
All right. Now, it is difficult to see that there is an appreciable change in speed straight down like this. It's also difficult to time it with a stopwatch. So the way I chose to show the difference in speeds between the smooth pipe and the gouged pipe is I put the pipes at an angle on the floor. Alright. Now my prediction is that when I drop these magnets down these pipes, the magnet is going to roll faster down the gouged pipe because the cuts in the pipe are going to interrupt the electromotive field that's generated by the copper pipe running against the magnetic fields generated by the magnet. Therefore, there won't be resistance in those areas. Therefore, the magnet is going to move down faster. Okay, it'll move down faster than the pipe that doesn't have any defects at all. So hold on a minute, I'm going to get a stopwatch. All right. All right, now first, I'm going to drop it down the smooth pipe. And I'm going to start the time. So here we go. Okay. The magnet took 5.93 seconds to go down the smooth pipe. Now my prediction, and I hope it comes true, is that it will take less time for the magnet to move down the nicked pipe. So here we go. 5.53 seconds. So my prediction came true. Now, in my report, when I conducted this test, I did each test 40 times. And 29 out of the 40 times, the magnet went faster down the nicked pipe due to the interruptions. Now, an argument can be made by doing it this way that there's also forces of friction acting. And of course, you might have been able to hear the magnet roll down the pipe. I attempted to, defray the effects of friction by cleaning out each pipe before I did the test. So, but you can make a good, reasonable argument that friction, didn't really have an effect on the test, when more often than not, almost over 70% of the time, the ball went faster down the necked pipe. Okay. Again, this is a test that just shows that there are defects present. Right? It's not a measure of the defects. It's not whether or not they're linear or how deep they are. That's more sophisticated. But what I hope I've done is successfully shown how eddy current theory can show that there are defects. And then, you can carry it further if you want to know, measurements of defects. So, thank you very much.